So, in this lecture we will see the instrument network analyzer. Already you are familiar with this picture. In a previous lecture we have shown this. I also described some of the network these functions of the buttons. Now, why do we need to test components? At microwave, components often used as building block, microwave frequencies. Now, we need to verify specifications like filters. We need to see how much harmonics it is removing, amplifiers, whether the local amplifier power is local oscillator power is sufficient or not, mixers, whether it is properly rejecting various signals. Also, suppose we are giving power to a antenna. Now, we need to ensure good impedance match, whether whatever power we are supplying to the antenna, whether antenna is radiating that. You see that if we have a poor match, suppose the left side antenna is not properly matched and you see 150 watt radiated power gets wasted, whether in the right side you see the same thing when which was radiating 150 watt, the same antenna is now with proper matching is radiating 1500 watt. So, the signal is received about 3 times further. So, that means if previously it was 40 kilometer, now 120 kilometer you can go. So, good match between antenna and RF amplifier is extremely important to radio stations to get maximum radiated power. Now, what type of devices are tested? You see there is lot of a large list, passive, active, various types of devices, various levels of integration. You see transistors, VCOs, receivers, RFICs, TR modules. TR modules are used in radars, then diplexers, duplexers, those are also radar or high power devices. Satellites also use them. Attenuators, adapters, dielectrics, many things are tested. Now, what is network analysis? Analysis of electrical performance of components and circuits used in more complex systems. What is vector network analysis? In microwave system, we want transfer of signal. We want to do it with minimum distortion, maximum efficiency. Now, for that, whether minimum distortion and maximum efficiency will be attempted, for that we want to measure, and that measurement consists of both amplitude and phase response. Either we can sweep frequency, that means we can give amplitude and phase frequency response, or we can sweep in power, that means amplitude and phase power response, which is also called linearity characteristic, because after some time if I go on increasing the power, the device becomes non-linear. So, that testing is also important, because that will give me an idea whether I will be able to do the transmission without any distortion in the signal. That means, quality of the signal should be kept. All of us know that for a linear network, criteria for distortionless transmission is that over the band of interest, my amplitude response should be flat, this left side graph, flat response in the band of interest, phase response should be linear in the band of interest. If this is there, linear networks give distortionless transmission. Now, what is vector measurement? Measuring both amplitude response and phase response of a network is called vector measurement. Network analyzers are available who does scalar, who are called scalar network analyzer. They don't measure phase response, they measure only amplitude response. Now, you see that magnitude and phase both measurements are necessary. Like S parameters, they are basically complex quantities. So, you need to measure amplitude and phase both for them. Impedance, we have seen that impedance is a complex quantity in AC circuits. So, you need to measure the impedance amplitude as well as phase, otherwise you won't get the idea of the reactive impedance. Then device modeling, we know that you have R, L, C, etc. So, that requires complex values. In time domain, if I want to characterize anything, I need to carry out a Fourier transform or inverse Fourier transform. Now, Fourier transform or inverse Fourier transform also is a complex operation, because the Fourier coefficients, if they are not done in complex wise, complex number wise, then there is problem. Similarly, vector accuracy enhancement, that is also a vector operation. Now, network analyzer, its predator was microwave benches. We have seen microwave benches in the impedance measurement time. Basically they work on standing wave. Network analyzers don't work on standing wave phenomena. They can separate incident, reflected and transmitted wave. So, they measures these incident, reflected and transmitted wave separately, and that is the beauty of network analyzer. Slotted line did not have capability to separate the incident, reflected, transmitted wave. That is why they had to rely on the standing wave phenomena. From that VSWR etc. concept came, but network analyzer, once it can separate incident, reflected and transmitted waves, it does not need to carry out all those standing wave phenomena, which are a bit complicated compared to the simple measurements done by network analyzer. Now, these are an thing that reflection phenomena. So, I have an incident wave, some reflected thing comes, some power gets transmitted. So, reflection gets characterized by this reflected by incident A by R. One of that is SWR. That time we have seen that the reflection coefficient and VSWR, they are quite related. S parameters S11, S22, reflection coefficient gamma, voltage reflection coefficient, power reflection coefficient, return loss, impedance, admittance. Similarly, transmission is B by R, that is given by gain or loss, S parameters, transmission coefficient T, insertion phase, group delay, etc. So, these are various parameters used to characterize either reflection or transmission of waves at microwave frequency. Scalar, example of scalar characterization is return loss, it is a scalar quantity. VSWR, it is a scalar quantity. Then example of vector characterization is impedance, because impedance is a complex quantity. Reflection coefficient, it is a complex quantity, it has both magnitude and phase. Return loss definition, minus 20 log rho, transmission coefficient, insertion loss, gain, these are the characterization of transmission. This is an architecture of 8510 network analyzer, a very popular network analyzer invented by Hewlett Packard company in early 80s, very successful network analyzer. 8510C. It had, this was the box, this was the controller, this was a test S parameter test set, this DOT, it has a source, then there were Pentium PCs with HPIB and buses. Now, basically how S parameters are measured by network analyzer? Network analyzer has its own source. It gives a source, so it gives the test signal itself and sees the response of the network. From that it infers the characteristic of the networks in terms of S parameter. It also has signal separation devices. I said that it has some directional couplers by which it can separate those signals. Then it has receivers for signal detection, a number of receivers, and it has processing circuitry, it has display. This is the network analyzer architecture. It is having source, source is producing incident thing, then the thing is given DUT is the network that you are trying to test. So, it is giving reflected. Now, it can separate this incident and reflected, as you see here that. So, that goes to two parts, incident and reflected, and then also it samples the transmitted one. So, this 3 is given to various 3 or 4 number of detectors, and then it processes and displays. Now, source of network analyzer, it have either a phase lock VCO, voltage control oscillator, or a synthesized source. Synthesized source means a source at a particular frequency, then from that various into 2, divide by 2, etc. So, that the source was having a particular range, but from that it synthesizes some other ranges. So, the source become a broadband source and gives lot of frequencies. Signal separation hardware, measurement of a portion of incident signal, then it takes a reference and it makes a ratio measurement. Now, if you make ratio of any measurement, then your error becomes less. Devices for signal separation, I earlier said directional coupler, along with that you can also have power dividers, but it has high insertion loss. Directional coupler is a very good, it has narrow bandwidth, low loss. Also directional bridges are used, but out of this directional coupler is one of the popular device for signal separation. Then detection, it uses diode detection receiver or tune detector. Now, averaging, same signal is sampled for n number of times. Average of samples, typically n is equal to 1024. VNA samples are complex. So, averaging improves noise floor. Any random signal, if you go on adding, its addition will ultimately give you something like mean of the signal. Now, noise has a mean 0. So, more number of measurements you average, your SNR will improve. Now, you see the network analyzer magnitude error is typically less than 0.1 dB, phase error is less than 0.6 degree. It has various, any measurement has some errors, no equipment is perfect. It has some systematic errors, some random errors, some drift errors. Systematic errors means, suppose I am saying that it should be defined at I want a perfect impedance match, but in reality I cannot always get an impedance match. I say that at the port the terminal should be defined. In actual reality the maybe port is extended a bit. So, all these are systematic errors. That means, errors in various assumptions we made, and while implemented that assumptions we did not keep, that is called systematic errors. Random errors we cannot say, mainly noise, etc., they give random errors, and drift errors after some time the performance degrades. So, suppose if I am to work for longer hours, my performance will degrade. Similarly, instruments, if they are worked longer, then their reliability degrades, that is called drift errors. So, network analyzer does a calibration. What is calibration? Calibration has three parts. Part to remove those systematic errors. For calibration, we need to first perform measurements with known standard loads or termination. For example, you can take a shot and measure reflection coefficient. You know, for a shot, reflection coefficient should be -1, but if you do it, you may not get -1, you may get 135 degree. -1 means 120 degree, but you get. So, then you know that your actual shot is not implemented. So, whatever you are thinking as a short, it is not a actual short. Basically, short circuit means it should be a thick metal, so that anything going there is fully reflected, any wave falling on it fully reflected. Now, if you have a thin metal plate, that also will reflect, may not be the with full reflection. So, this is an example of a systematic error. You have open, there also the reflection coefficient should be +1, but you can have an open who is not giving +1, it may giving 130 degree. So, that you can then, so this performing measurements with known standard termination, you can estimate systematic errors from observing errors in such measurement, and then you can correct for those systematic errors in your measurement. That means, now when you will take the actual measurement, you will remember that these are the errors. So, you can do error correction. This whole process is called calibration. Network analyzer does this calibration. If you remember your oscilloscope, there was also a calibration. What? That suppose oscilloscope is measuring something, how do you know that it is correct measurement? So, you give oscilloscope had a 1 kilohertz square wave signal. So, you put that button, nowadays in the back side of oscilloscope it is there, earlier days it was at the front side. So, you press that button, you get 1 kilohertz square wave, but you measure, you may see that 1 kilohertz and I think 1 volt peak to peak or something. So, you can then check you are not getting 1 volt peak to peak. So, you adjust your knobs, so that it becomes 1 volt peak to peak. Then you see that time period is 1 kilohertz, means 1 millisecond will be the time period, but it may not be 1 millisecond. So, you correct that. That is called calibration, that with a known thing you do. Here the known thing is some standard termination, then from that you estimate systematic errors, and in actual measurement you correct for that. This is called calibration. Now, vector error correction, if you do this model, 12 error terms are corrected, requires capability of measuring both amplitude and phase, requires calibration standards with known precise electrical characterization. So, you see that data before correction is this curvy curve, but after correction, error correction, it may become something like this. So, this frequency response and this is an erroneous frequency response. So, you see that return loss with frequency, ideally it should be like this, there should not be any bump, with frequency there should be a frequency response, but a typical thing is you get like this, with error correction the whole thing becomes this. That is the beauty of network analyzer, that it can do calibration, and by that it can eliminate various errors in measurement. Bench based measurement could not do that. This is a detailed view of this. One thing it says that you see there are so many channels. So, that is why there are generally 4 receivers are there in the network analyzer. Some designs instead of 4 it can have 3, then that is a bit less accurate, but in good network analyzer you have 4 receivers, but 4 receivers means obviously 4 microwave receivers are quite costly. So, network analyzer, that is why it is a costly equipment. Measures S parameters as ratios of complex voltage amplitude, that means it has a reference, with respect to that it calculates various ratios. Any time you also remember this, that suppose some quantity I directly measure and that same quantity I take a ratio with respect to some standard thing. Now, the ratioed measurement always is a better measurement. Unfortunately, the terminal planes of voltages etcetera, they are inside network analyzer, because you see when you are extending a port, definitely network analyzer is sitting inside. So, his port definition is different. What we are seeing as port is not always his port. So, that is why he commits some error, that is get corrected in the error correction. It was all about network analyzer, its basics, and what you can do basically with that you have 2 ports. So, you connect your device between them and then you can measure your S parameters of the device for a 2 port network. For an N port network, you need either an N port network analyzer. So, generally 3-4 ports are also there, and typically up to any microwave frequency. Nowadays, even 550 megahertz, 550 gigahertz, up to that you can measure various networks. That thing, even people are trying to build up 1 terahertz network analyzer in Hewlett Packard company, sorry, presently they are called Keysight Technologies. That company has in Japan, in Tokyo University, they have made one such 1 terahertz network analyzer. So, you see that this technology can go up to 1 terahertz, still this same network analyzer, this same principle they work, and they find out the S parameters of those networks even up to not only in gigahertz, 1000 gigahertz, that is 1 terahertz. So, the second tool, that S parameter, that helps to characterize any microwave network, and the network analyzer is the equipment by which you can measure that. With that, this part is concluded. So, we have seen 2 tools. The first tool was Smith chart. The second tool in this series of lecture we saw as S parameter, and with this we will see in the next lecture some problems based on these S parameters, and that will conclude the lecture of this week.